to the evolution equations and this one, right? And for LTV models, the metric functions, for LTV models, we have to integrate this. For Sekeres models, these constraints will also have to be integrated, but will be more complicated. Because for LTV, these constraints are differential equations on the radial variable. But for Sekeres, this will be differential equations for all the variables. So the answer is we recognize different models by looking at the constraints. We have to work these constraints. So the techniques, are the standard techniques when you have a system of hyperbolic partial differential equations. You have to work out the constraints, solve them, and then propagate, right? So, example, Kantowski-Sachs, DOST. How long we have? I think we already passed.
Yes.
Yes. Well, let me just show you this one, and we finish. Okay. Kantowski-Sachs with non-zero lambda. This is the metric. This we've seen in a Maple worksheet. See? Kantowski-Sachs with non-zero lambda. Yeah, this is the end, the last one. Now, what we can see, we can compute the electric Weyl tensor for the Kantowski-Sachs and substitute in the 1 plus 3 equations, and we obtain this link. This means that psi2, which is the scalar that characterizes the electric Weyl tensor, can be obtained by an algebraic constraint. Therefore, we can remove that equation. We don't need that equation. Because it's already, we can obtain psi2 as a constraint. Therefore, these are our equations. The 1 plus 3 system reduces to these 3 equations and this constraint. And that's it. Kantowski-Sachs, that's it. The difference with FLRW is that FLRW would not have this one, would not have this term or this term. But Kantowski-Sachs is like FLRW with a shear equation, right? Now, the dynamical system, this is what we did in the Maple worksheet. We introduced these variables, and we obtained a very nice dynamical system. This dynamical system we obtained, which we showed in the Maple worksheet, right? You remember? So this is a dynamical system. It's a 3-dimensional phase space parameterized by, except that we did it for lambda equals 0. If you do it for lambda greater than 0, you obtain this dynamical system. This is DOST. Remember, this is DOST. Okay? That's why the equation of state is P equals 0. Okay? So this is what we obtain. So in this case, for Kantowski-Sachs, the 1 plus 3 formalism leads directly to a very nice dynamical system. Okay? And then, for next time, spherical dust models. We can see them very quickly. Let's finish them. Okay. Okay. So, oh no, you are tired. Maybe we continue that. And now we've seen in general how the somebody sent me an email asking for the files, the metric files. In fact, the metric files you can they're very easy. You can do them by yourself, but I can show you how to after when we have a break. I'll show you how to make this metric file.
No, in afternoon leave.
In the afternoon there is a session.
We can have session for that.
Okay, fine. So now we've seen now how you can understand Einstein equations as a first-order system that is constructed in terms of covariant quantities that are defined by the flow of a four-velocity. And we were also, we saw how different models can be obtained from this method. because for example, if you take shear equal to 0, you put that in the equation, then you get shear-free models. If you remove the acceleration and remove pressure, then you get the equations for dust. And then how do you distinguish between, that's what I explained already in the last lessons, in the last, I think that was the last slide. You have many dust solutions, so how do you distinguish which one? The information is given to you by the constraints. The constraints themselves tell you all the information. I think that was in the last lecture. The last slide, for example, showed you how if it is Kantowski-Sachs, then the constraints are trivial. But if it is because, but that is because the constraints involve spatial gradients, and if the metric is only dependent on time, then these spatial gradients will be trivially 0. So in the case when the models are not homogeneous, then these constraints have to be solved. And these constraints are the ones that allow you to identify different types of solutions. See, what I'm saying is important because you can have solutions that have the same evolution equations. Exactly, exactly the same evolution equations. But remember that this is a system of partial differential equations. Therefore, even though the time derivatives may be identical, but the spatial gradients are not. And the difference between one solution, one type of evolution and the other is given precisely by the constraints. See, it's like a system of partial differential equations. What I'm saying shouldn't be of any surprise to anybody. Anybody who has seen systems of partial differential equations know even if the time derivatives are the same, but the space derivatives are not the same. So solutions are going to be different. How you distinguish them? Well, by looking at the partial differential equations that involve the space variables. Now, following these constraints from the 1+3 system, you can also derive LTV models, right? However, I have shown you how you can derive these models from the Lemaitre formalism. Do you remember? We saw the Lemaitre formalism for spherical symmetry. There, LTV models appear immediately as the subclass for dust. So what I'm going to do now is we're going to explore these models in their standard variables. These models are very helpful. They have multiple applications and uses. In fact, I think that if you go to Google and type LTV, you will get a lot of entrances. They are very popular models. And essentially, they are popular because if you want to model, if you want to study anything under inhomogeneous conditions, then these models are very nice because they are mathematically tractable. You can get analytic solutions, or you can get results with very simple numerics. See? So I think that these models are, I'm sorry, I've been irritated in my throat. I should have brought some pills I have for this. Okay, it's an important thing. It's an important tool you should have in your toolkit if you are going to do any work on relativity, general relativity, either cosmology or quantum gravity or inflation or gravitational waves, whatever. This is a nice case of exact solutions that you should know about. You should have some minimal working experience with them.
Most popular model for dust collapse.
Yeah, also. Yeah,
The only model, the most
Yeah, when people study the so-called spherical collapse model, it's done with these models. Well, but they do it with Newtonian physics. So it's not exactly LTV models. The astrophysicists use dust, use Newtonian dust, which is very similar. These models are very similar to Newtonian models, but they have more degrees of freedom. Of course, the astrophysicists will say, no, I don't care about these degrees of freedom, that's science fiction, reality, reality, reality. But no, they're wrong because sometimes small effects can lead to big changes. Remember the perihelion of Mercury? It's a very small effect. And all the conservative people say, no, forget about that, that's nothing. We'll find out. We know everything. Open champagne bottles, physics is done. All students have to do is calculate more orders of magnitude. And it turned out that this small effect leads to a big change.
No, but gravitational collapse is fully relativistic. Why? There is Newton.
No.
Tolman-Bondi model.
Yes, but what I'm saying is the people who study astrophysicists, open any textbook, Padmanabhan, typical text.
No, I'm talking about Landau-Lipschitz classical theory of fields.
Yeah, no, but there is a confusion because the equations, the LTV equations, look very similar to Newtonian equations. In fact, formally identical.
That is right.
Formally identical. But the concepts, but it's a different approach, even though sometimes the equations can look very the same. But the interpretation of the terms is different. And also, the collapse models that are used by astrophysicists, either Padmanabhan, Landau-Lipschitz, and all of them, well, I think, no, Landau-Lipschitz is presenting the LTV directly. But that's a book on general relativity.
Yeah.
And that's not what the astrophysicists do. Astrophysicists do is Newtonian. Now you can show that these Newtonian equations are very similar to the relativistic ones. But the relativistic interpretation of the terms is different, and also the relativistic equations give you some degrees of freedom that are not available in the Newtonian framework. So it's a small change, but nevertheless, what I'm saying is that even though there are small differences, you shouldn't think that sometimes small differences can be important. Okay, so let's look at the models. See, this is the lecture today, LTV models. So we're going to see basically the models in the usual variables. These usual variables are interesting because they look like Newtonian dust. And then we're going to introduce a Friedman-Robertson-Walker-like parametrization. What I mean by this is that the metric, it's always possible to change the metric by coordinate transformations or by relabeling the variables, by renaming, reparametrizing the variables, and then the metric can look like something. Now, one has to be careful because this might not be coordinated. This might be something tricky in the sense that you modify a metric so it looks like something, but that doesn't mean that it is like something. It might look like something, but to see if it is similar, you have to compute covariant quantities. Covariant quantities are independent of the coordinates. Therefore, they are honest in the sense you compute that, then whatever you compute is independent of the coordinates. But the metric is not. The metric is something that is completely dependent on the coordinates you choose. You have a metric, you put coordinate transformations, the metric changes completely, and that can be misleading. One typical example is Schwarzschild. Schwarzschild, are you familiar with the Schwarzschild metric? Yes. Okay, you realize that in the standard description, the metric coefficients are independent of time, right? because we say it's a static solution, static vacuum solution. Now, what if I show you some metrics in which Schwarzschild appears dependent on time? And I tell you, this is Schwarzschild. You've never seen the other ones. So you would believe, by looking at the metric, that it's not a static solution. See? But this is cheating, because once you compute put the condition for a killing vector, you will see that the metric admits a killing vector. Then you would conclude that the time-dependent metric is not that the time-dependent metric is useless. It can be useful, but you can conclude that it's writing up a static metric in some phony coordinates so that it looks non-static. Okay? Now, having said all this, I hate when this happens. Anyway. Okay, the standard representation of LTV models, it's this metric. This metric we have already obtained from the Lemaitre approach, except that the function k that appears there, now it depends only on R. If it doesn't depend on R and we have a function n, then it would be a general spherically symmetric solution. But the fact that n that was here is now 1 and k depends only on R means that it is a DOS solution. Now, the dynamics, this R, the function here R, which is the only time-dependent function, is found by solving the Friedmann equation. We have to solve this Friedmann equation. For the moment, I'm going to assume cosmological constant is 0. Okay. So we have to solve this equation. This equation leads to this quadrature, which is actually this quadrature can be solved analytically. I'm going to show you some analytic solutions. Now you see here this function m. This is a mass function that we have seen before, that Lemaitre discovered. It's a function of R. Therefore, this integral is well posed, because you could ask me why this integral cannot be done in general, because k and m, if k and m are functions of t also, then this integral is not well defined. Here it is well defined because you are assuming it's an integration over big R, but big R depends on t, while m and k don't depend on t, so they can be taken as constants. See, along for an observer that is co-moving with this dust, will keep the R coordinate constant, right? So m and k can be thought of as constants, so this integral is well defined. And this function here, TBB, is a function of time, is integration constant. It's integration constant, but it's not a constant really. In general, it has to be a function of R. Remember, these are partial differential equations. Okay. So it's a function of R, and it is the Big Bang time. Why is the Big Bang time? Because R is 0 when time has this value for all R. See? Now, here is a conceptual hurdle here. So you say, come on, the Big Bang time is constant. You are telling us the Big Bang time is not constant. Well, yes, the Big Bang time for inhomogeneous models, the Big Bang doesn't have to happen simultaneously, right? So get used to this. It's the Big Bang in a homogeneous model. In a homogeneous model, everything depends on time. So a given event like the Big Bang will happen at a fixed time, because there is no spatial dependence. If you have spatial dependence, then many events will not be simultaneous. That is, they will not happen. Remember that simultaneity is also a relative concept. It depends on your frame, your form velocity. Here, every statement I'm saying is strictly referred to the comoving frame, right? Comoving frame. In a comoving frame, the Big Bang, that is the coordinate times that mark the singularity, need not be the same. The singularity can occur for different observers at different times. Okay? Specifically, this happens with LTV models. That's the first important difference that you can appreciate with respect to homogeneous models. Okay? Now, let's go on. Okay. Analytic solutions of the Friedman-like equation. See, this is a Friedman-like. I'm going to call this Friedman-like equation because it looks like a like a Friedman equation. Remember the Friedman equation we had here, A dot. Here we had a density. Here we had A, and here we had a constant curvature. Do you remember the Friedman equation for FLRW models? Yes, do you remember it? So this looks like, it's not exactly the same because R is not really a scale factor. R is the radius of the two spheres, is the radius of the orbits, right? A scale factor is a quantity that is a local quantity that is telling us how local distances magnify or contract, right? R is not a scale factor. R is the radius of a sphere. If it's a small sphere, then it's a local, but it can be a very big sphere. So it's not really a local quantity. See? Okay? So we call it Friedman-like equation. So the first solutions are if k equals 0 for all r. Remember that k is a function of r. So this statement, k equals 0, means for all r, or at least for a continuum values of r, for a region, right? If it is 0, this is the only case that allows for an explicit solution. And the solution is essentially proportional to t minus Big Bang time to the 2/3, right? This is very similar to the Friedman equation for dust. Let me write it this so that in order to compare the chalk.
रोज बोलना जाके वो लाइट चालू कर दे
See, this is the equation, the Friedman-Robertson-Walker equation. See, here, cosmological constant is 0, so it is this integral. See, so look how it is so similar to that one. This in the other one, what we have is r dot square, and then here we have something like 2m over r minus k. But this is a function of r. So it's very similar. So it should have mathematically similar solutions. But it's not the same. Why is not the same? Mainly because this is an ordinary differential equation, and this is a PDF, right? This is important. It's important. See? So what happens if this is 0? This is 0, then this immediately solve this thing. We take square root, and this thing becomes, right? Okay? And this is simply see? then everything follows. What you get is something like A proportional to T to the 2/3, right? But we can identify, we can also write it like this. Right? Because there will be an integration constant, but constant, an integration constant. And that integration constant is a constant Big Bang time. See? It cannot be otherwise because it's an ordinary differential equation. So the Big Bang time cannot depend on radius. If you are working with an ordinary differential equation, and the independent variable is t, then your constants cannot depend on r. They have to be constants, right? Okay? Now here, we get the same thing. But hold on, here it's a partial derivative. Here it was a total derivative, right? So, right, and this is going to be right. So you get something similar. But now this thing is a function of r, right? Okay.
But
So-
this happen if dr by dt, r dot is greater than 0.
What?
R dash is greater. You avoid cell crush.
What?
Cell crush. You avoid cell crushing.
No, but you r prime. You
Yeah,
mean
R
r prime? No, but let's skip that.
Yeah.
Let's first clear this thing. Okay. We'll see that. Okay. So obviously, the evolution makes sense for t greater than t Big Bang, and the same thing here. The evolution has to be larger than this thing. So if you make a coordinate diagram, here you plot t, and this is r, your comoving observers will follow this. In this coordinate diagram, your comoving observers will follow these world lines, right? For t greater. Now, what is the Big Bang time? The Big Bang time is some sort of surface here. See, this is TBB of R. So you see that the Big Bang time happens at different times for different observers. This function is not completely arbitrary. As Sushan said, you have to choose it in order to avoid another singularity called the shell crossing. But for the time being, forget about that. Now, the only thing is that here, what you have when t equals TBB for some r, you are here, and radius and the curvature and the radius of the two spheres of the orbits of the group are 0, right? This is difficult to understand. Don't see when you are faced with a difficult concept. Don't put resistance. Let the concept invade your mind. Later, you get used to it, and you start understanding it. But some people, they see a concept that looks unfamiliar, and battle it, take the sword, and try to battle it. Then it's worse. Don't, just take it now. Take it. It's a fact. That's the way it is. Later, you assimilate that, you understand it, okay?
Excuse me, you have said that these two equations are similar, that
Yes.
Riemann and Cosmological, and then I have missed some of the things. What do you then afterwards you are doing here in this equation?
Here?
No, there.
Here?
Then little
Here.
bit, yeah. What you are doing in left hand side, dA by dt, So you are integrating or what you are doing?
Yeah, I'm integrating.
You are integrating,
Yes,
no?
yes, yes.
Okay, okay.
Yes, because this differential equation, I have this differential equation. This is a trivial integral. You just have, this is a trivial integral.
Yeah, you are integrating, no? Yeah. You are integrating and finding the solution.
Yes.
Okay, okay.
That's all. That's
Okay,
all.
okay.
Nothing more. Again, sometimes you do simple things. You look for the simplest explanation.
Yeah.
Don't. I'm not fixing the universe. I'm just humbly. It's a humble differential equation. It's not the equation of the creation of the universe. No. Nothing like this. Just a simple differential equation. Okay. So this to illustrate how they are similar, but now there is one thing. Is this the only solution, or there is another solution, mathematically speaking? What happens if I change signs? Well, what I'm saying is that this would also be a solution. This is also a solution. But it would have a different interpretation. Because this solution would only be valid for times smaller than TBB 0. So what would be this? As time goes on, the spheres become smaller and smaller and smaller. So what's this? Collapse. Right? So these solutions can describe expansion, right? Or collapse. Both of them, right? Both of them. And the same thing here. The same thing here. This is collapse and this is expansion. But of course we would have to reverse them. So the same solutions can describe collapse and expansion, but we're not interested in the collapse part, so we'll just consider expansion. Okay? But they can. Now, this is a very simple case. These are whenever we have k equals 0, this is the parabolic evolution, k equals 0, and it's very similar to spatially flat FLRW, right? And in fact, you can show that, we'll see that, if this k is 0, that means that spatial curvature, there is a Ricci scalar of the rest frames, is 0. So they are also spatially flat, okay? When I say rest frames, you know what I mean when I say rest frames, right? Yeah, everybody knows what I mean, right? No? There's some no? No? Didn't say no? Okay. So, these are very simple. These are very simple, but these are the only ones in which the solutions are explicit. For other cases, the solutions are not going to be explicit. For example, here, we have the hyperbolic evolution. See? And this is a negatively curved rest frames. The rest frames have negative curvature. And then we have either these two parametric solutions, right, where the parameter has to be greater than 0. Again, we are only considering expanding cases, not collapsing cases. Okay? For collapsing cases, you would have to reverse the signs here. But we're not going to see it. Right? So, again, this is the Big Bang time, because eta equals 0 is the Big Bang. So eta equals 0 means that t equals t bang bang, Big Bang. And so these are the solutions we obtain, right? It's a parametric. And we can also obtain an implicit solution that gives you t as a function of r. This can be inverted with Lambert functions, but It's it's horrible, right? What you get is this explicit formula, where z is this function. It is t is a function of r, of this algebraic combination, where z is this one, square root here, arc cosine, right? This is an analytic solution, it's an exact analytic solution, but it's given in implicit form or parametric form. Then, this is the case where k equals negative. Notice that if k equals negative, then this a plus sign will appear here, and then r dot is always positive. Okay? Cannot change sign, right? Because the right-hand side is positive, okay? And it's a square, right? So now this is one case. This is the hyperbolic negative curvature, and it is very similar in the same way, bears the same relation as the FLRW DOST models with negative curvature. These models are often referred to as the open model. See, normally FLRW models, you have the flat model, which is that one, right? The open model, which would be the equivalent of this one, and has very similar solutions. In the FLRW case, the solutions are very similar, except that n, k are constants, are some constants, okay? But otherwise, the solutions have the same mathematical structure, because we're dealing with a case of a partial differential equation that looks very similar to a total differential equation. Therefore, the time part of the solutions are similar. The big difference are the integration constants, and the parameters are no longer constant. But otherwise, the equations look very similar. Okay? Now, this is the elliptic. The elliptic evolution is if k here is greater than 0. Notice that if k is greater than 0, then r dot can be 0. What's the meaning that r dot is 0? Remember, r is the area of the orbits of the two spheres. So it starts to increase. Suddenly r dot is 0. What happens? It bounces. It bounces. So these are solutions that expand and collapse, right? Necessarily. They necessarily have to do that. As long as k is positive, they have to expand and bounce. Now in an FLRW solution, since m and k are constants, this means that in an FLRW solution, all points for all observers, they will expand and then bounce and collapse. But notice something. LTV models are inhomogeneous. This inhomogeneity is patently manifest in the fact that m and k are not constants. They change from observer to observer. So the question is, can you set up a model in which k, let's say k for around r equals 0, a neighborhood around r equals 0, k is positive. So for all those co-moving observers that are in this neighborhood will expand, bounce, and collapse. However, we choose a function k so that it becomes negative for other observers. So here what you would have is an inner spherical region where observers expand and collapse, and this is smoothly surrounded by a region where the observers never collapse. They continue expanding. Do you realize that this is possible, and this is also very simple to do? All we need is to choose a function k so that it is positive near the center, near r equals 0. Then it starts decreasing, becomes 0 at one point, and then is negative. So this is a very simple description of a region that is collapsing and therefore will be forming a black hole. Thank you. Region that is collapsing and therefore forming a black hole that is surrounded by an envelope that is perpetually expanding. See? And this is the collapse model that Sushan was talking about, that you can construct. It's a very simple analytic model of a structure that is collapsing, surrounded by an ambience that is always expanding. Can you see that this is really possible to do with these models? Is it clear?
Sir, these are astronomical models, sir. They are celestial, you might be finding them in the universe. All
What?
these models are the mathematical interpretation for the different models that, for the different systems that we find in the universe. Is this the case?
Well, they're extremely simplified models because you're thinking of a galaxy. Galaxy is not spherical, right? So first you assume that the galaxy or the object that is forming is spherical. And then objects are rotating and it's an extremely simplified description of how astronomical bodies form. However, notice that when a galaxy is forming, it does not end up into a massive black hole. Massive black hole in the center only. See? But the galaxy itself will be an ensemble of stars and gases and so on. So these models don't allow for that. These models, the way I described, in the sense that we have an inner region that is collapsing, but necessarily will form a black hole. In all that inner region will terminate into a black hole. And this doesn't happen. When structures in the universe are forming, they start collapsing, but at one point the collapse stops and you have a stationary system. Probably internal black holes will arise there, but not the whole system will be a black hole. You agree? So these models offer you a description of structure formation up to a certain stage. Because imagine a realistic scenario of structure formation. You have dust that is starting the whole thing expands, but a chunk of it will expand slower and slower and slower. The rest will be expanding faster, faster, faster. And this thing that is expanding slower starts to collapse, right? And at one point, when it starts to collapse, the dynamics is very simple. It's essentially radial motion, right? But once this thing reaches a respectable density, it will not be just radial motion. The motion will be very complicated, right? You will have rotation and the orbits, or the particles will follow very complicated orbits and so on. And it becomes extremely complicated to describe. It has to be described by numerical simulations. Now, at that point, obviously, these models break down. Because these models are spherical, they only allow for radial motion, right? So yes, these are toy models that are very handy to describe the initial and middle stages of structure formation, but not the final stage. Okay?
Yeah, there is one. You mentioned that if r dot equal to 0, then it will start bonus, r will
It will be a bounce. R dot equal to 0 is bounce. R dot.
R dot, that means dr by dt equal to 0.
Yeah.
But it doesn't mean r equal to constant.
Doesn't mean what?
R is equal to constant.
At that time, no, because there is radial dependence. It's a partial system of partial.
Okay.
R dot equals 0. is a condition that is radially dependent.
Radially dependent.
Yeah,
okay.
because it's a system of partial differential.
Yeah,
It's
so
a partial differential.
partial,
equation.
yeah.
It's not a total.
Total, yeah.
In FLRW, yes.
Yeah.
R dot, A dot equals 0 is a constant.
Is a constant.
Happens at a constant time.
Yeah.
That's a good question, but the bounds in FLRW models does not happen at a constant time, right? Not only the Big Bang happens at a different time for different observers, but the bounce itself happens at a very different time for each observer. Each observer has a bounce at a different time.
Sir, why do rotating galaxies have their arms stretched out when rotating?
I don't know. No, honestly, I don't know. Probably it's a feature of stability, dynamical stability, but I don't know. Really, no, I'm not joking. Don't know.
It appears as if a ballerina is trying to balance herself.
Probably, I think that's an issue of stability, the more stable configuration. But then, it's a very simple diagram that we can do to understand all this. It's as follows. Here, we can study the solutions of this equation, See, the equation in question is this one. We have, and I am going to write the partial differential equation so that it is absolutely clear that it's a partial differential equation, right? Right? We're looking at the solutions of this. And I show you the analytic solutions. Very good. Okay. How we can solve them? These solutions are given in the coordinates t, r. First question. What happens with the coordinates theta phi? These coordinates were ignorable, right? So, because nothing depends on them,
Yeah.
right?
It's a spherical symmetry.
Spherical symmetry. So we don't need them for the dynamics. All the dynamics. But remember that it is a four-dimensional system. It's a four-dimensional system in which to every S2, to every point in S2, there is a plane parameterized by T and R, right? Right? It's a four-dimensional system. There are two dimensions here and two here, right? So for every point here, we have a dynamics here going on. But if we take another point here, we have identical dynamics here, right? That's why we don't need the two spheres, right? Because we can study the dynamics in the subset TR. And the dynamics for the subset TR is the same for every point with theta phi, right? So what happens is that in this diagram, this is a TR diagram. The TR diagram, every point really represents a whole two-sphere. Because what happens here, this is an event here, right? This is an event here, but this event could have happened everywhere in the two sphere. Do you get this? Okay? So the fact that we are looking at the dynamics in 2 dimensions does not mean that the space-time is 2-dimensional. It's 4-dimensional. Or it's 4-dimensional, but all the dynamics takes place in only 2 dimensions, radius and time. Now, because of spherical symmetry, what you have is, remember, you have 2 spheres, or orbits of the group. They can be expanding, contracting, expanding and contracting, expanding very fast, very slow. But the only motion that is taking place there is radial motion, right? If you are seeing it physically, if an LTV model is working its way there, all you would see, and you put markers, little quarks. What these quarks will be doing is radial motion, right? Here you have a 2-sphere, can you imagine that? 2-sphere, and the quarks would be moving, right? Now, all the quarks will be moving in the same way. See, quarks will be moving in different angles. But because of spherical symmetry, we can only take one of the quarks. Because we know that the other quarks will do the same thing, right? In terms of time and radius, right? Okay?
Question?
Yeah.
If one of those
Quarks
quark has angular velocity, so it
No,
violates.
there is no angular
suppose,
velocity.
So suppose it has an angular velocity, then it violates
It violates, yeah.
the spherical
If-
symmetry.
Yeah,
if one of these quarks starts twisting, it's no longer spherical symmetry.
Yeah, spherical.
So strictly speaking, it's only radial motion. That's why, answering your question, if you have some cloud that is going to form a star, or not a star, a galaxy, at some point you can say that purely radial motion is a good approximation at some point. But there comes a point it's not. There comes a point that this cloud, as it's forming, there will be angular velocities, twisting, and so on. Then this is no longer a good approximation, right? Okay? So we study developments in the TR coordinates, right? In the TR coordinates. Yeah, understood? Okay? So what happens, let's say one case, K equals 0, and T Big Bang is, let me say, I'm going to invent this, it's something like 1 minus I don't know, minus r squared, minus exponent of minus r. I'm inventing this, right? So this function here will take this form. No, something like this. Minus. Well, what I want is the function to be doing something like this. Whatever. We choose a function. Right? It's going to be doing something like this. Okay. So if k equals 0, this, what happens with the observers? What they have to do? They can only expand. Right? If k equals 0, then r dot is always positive, right? It's always positive, right? So the co-moving observers moving like this. That's what they will do. That's all. They will be moving. Now, what happens if k equals 0? See, this here, it's r equals 0, right? R equals 0, okay? Because that's where t equals t Big Bang. See? So r equals 0 here. Here, singularity, Big Bang. Okay? You are fried if you go there. And that's what they do. And as they move along, we're going to see that you can also set up this border line that is marked by r equals 0. We'll see that r is also 0 here. R is 0 because this is the center of the spheres. This is a fixed point of the orbits, right? There's a center. So essentially, this is the surface r equals 0. This is the surface r equals 0. Now, the surface r equals 1 would be something like this. This r equals 1. Then r equals 2. Etc. R is increasing, okay? So this is the solutions. In fact, as a homework, I can supply to you forms of M and T Big Bang so that you can plot this. We'll do that. We'll do that. These variables are not, because you are going to tell me, how do you choose M? Well, not a simple question. How do you choose a Big Bang function? The traditional variables, they don't help you. But I'm going to show you some variables in which the choice is very straightforward. But for now on, just think of that. What I'm saying is that r equals 0 here. It's possible. The important thing that you see is that here, with a choice of function with k equals 0, r dot necessarily is greater than 0, right? And so the only thing the observers can do is to expand. That's all. And then, as they expand, each observer will reach different values of r. As they evolve, r will be increasing for them. But the constant value of r will be reached at different times for different observers. See? Okay? There is nothing more, there's no more mystery. One interesting thing. What if k equals 0, how is this velocity? This is the velocity of the radius of the orbits. See? What happens with this velocity as r goes to infinity? It goes to 0. So here we can also plot, another thing we can plot that is very nice is this. Another thing we can plot is this. See? We are going to plot r as a function of t for different values of constant r. So here we have r equals 0. R equals 0 remains 0. See? This is the central value. The center. The center, see, I'm at the center of the explosion, right? So my radius, see, the radius, see, if you have a rotation, there is a point in the center that is fixed, that is not affected by the rotation. And what's the radius of the orbit for that point? 0, right? So that's it. This is the center. R equals 0. R equals 0. Now, the one that is very close to it will be expanding here, starts here, and it will be expanding. Right? In fact, let me do it like this. Okay. The one, let's say this is r equals 1, r equals 2, r equals 3, r equals 4. Okay? So the one at r equals 1 is doing this. Right? The one at r equals 2 is going to be doing, it starts here at some time, no, the Big Bang time, this is more complicated. Yeah. Let me do it correctly. This other one. The other one. Right. This is r equals 1, r equals 2, r equals 3. Right? See? Notice that they, as r goes, the time, the Big Bang time is before, right? And do you see? This one, the Big Bang time is before this one. The Big Bang time is before. The Big Bang time is before. See? So they start from times before. See? And they all expand. But they will reach any constant value of r. See, let's say this is r equals 3, is reached at different times for different observers. Right? But all of them, they simply expand. That's all they do. Okay? Clear?
So what are the parameters for choosing K?
We'll see that. We'll see that. For now, only you need to see is that you can somehow choose them in a good way, in a physical way. But for now on, just think they are functions. K will be one function. The condition is that these functions are 0 at r equals 0. That's all.
And what is M? M is a function of R, capital M.
M, yeah, capital M.
But what is, how do we get it some physical, some physical meaning of M?
We'll see that.
Okay.
We'll see that. We'll see that. It's what is called the quasi-local mass.
Okay.
It is a mass. It's a sort of mass.
Sort of mass. No? Yeah.
We'll see that.
Yeah.
We'll see that.
And
But see, the task now is that you get the feeling of the models. You get the feeling of the solutions, what they say, what happens, what they do. And then all these things will fall into piece.
Yeah.
Okay?
So capital R is a function of small r.
Yes?
Yeah, and
T-
r theta phi is a spherical coordinate. Small r theta phi.
Small r.
Theta phi, they are,
Yes, they are spherical coordinates. But
and
remember, they are co-moving coordinates.
co-moving. And capital R is the radius of the
It's the radius
system.
of the series, of the
Yes.
orbits. Of
Or,
the,
and it is dependent on small r. Okay.
yes, and on T.
Oh, no, yeah, that's right. Yeah. That
But-
means here
so-
Big Bang time is relative.
Yes.
Means it's not absolute. It's not same for everyone.
Yeah,
Yeah.
Big Bang is not the same for everyone. As you can see here, this observer have Big Bang times are different.
Yeah.
Okay. Now, part of your and this is the point that is shown here. See, notice here that a model, a unique model, is specified if you choose M, K, and TT, and TBB. If you choose these functions, you have a uniquely specified model, right? So you have 3 parameters. However, strictly speaking, only 2 of them are necessary, are strictly necessary. But forget about that. Now consider that you need 3 models, 3 parameters, which are functions of R, to specify a model, right? Because we're dealing with a partial differential equations on 2 variables, time and radius, then the initial conditions have to be functions of radius. This is the same if you solve a partial differential equation that depends on T and R, your initial conditions are functions of R. Well, that's exactly what happens here, except that you need 3 functions of R to specify a unique model, okay? Now, here, this is the case with K equals 0. K equals 0, that's it. That's all what happens, okay? The difference is that as if k equals 0, then r dot goes to 0 as r goes to infinity. That is, these curves eventually, see, they are decelerating, right? They are decelerating because r dot is going to 0. See, r dot is the slope here. So this slope will start going, they're like logarithmically, they're growing logarithmically. Okay, now, what happens if k, we already saw the case k equals 0. So what happens if k is negative? If k is negative, then we have the same thing. Except that these things would grow much faster because r dot goes to absolute value of k as r goes to infinity, right? So these curves, they expand, but much faster than the others, right? Because in the other ones, r dot tends to 0 asymptotically. See, remember, r dot is the slope of this curve, right? So what happens if the slope tends to 0 asymptotically, right? But in this case, the slope does not tend to 0, but tends to a positive number, asymptotically. Therefore, we have qualitatively the same behavior, except these observers expand much faster, right? Differential equation. Look at it as a differential equation. This differential equation, the solutions, if you plot r as a function of t for small values for constant values of small r, what you will get is this curve expanding faster.
So means here you are telling that no r dot goes to 0 as r goes to infinity.
Yeah, and here goes to a constant, right? But otherwise, it's the same qualitative. Qualitatively is the same. You have observers simply expanding from a non-simultaneous Big Bang. The non-simultaneity of the Big Bang shows here, reveals here, that observers emerge at different times, right? And they expand. The only thing they can do is to expand, but they will expand faster. That's the effect for negative k, is that observers, that they expand faster. What means expand faster? That they take less time to get large values of big R. It takes them less time to do that. Expand faster. Right? But otherwise, it's the same thing, right? Qualitatively, it's exactly the same. Okay? Now, let's see the case. Now, we're going to see the case.
Sir,
Yeah.
by taking k negative, we are assuming k is also constant here.
What?
We are also assuming the k is constant here, negative number.
No,
Or-
k is
or-
negative. K is negative, period.
And increasing with r, or it is constant.
It doesn't matter for what I'm saying. It doesn't matter. As long as it's negative, all what I said remains. Of course, k, you are asking a good question. K is negative, but should it be increasing or decreasing? We'll see that.
In both cases, it will expand.
Look. I said that before. How do you choose these functions? We'll see that. I don't want to open a huge parenthesis because then you forget this, okay? So we'll see that. Be patient. We'll see that. There are ways to choose them.
Now you have to see about that integration. Integration plus k and minus k is totally different.
Yeah, no,
That's what you have to understand.
No, that's exactly. See, that is revealed in the form of the function.
Yeah, that's what I'm saying.
That is revealed in the form of the functions. However, I'm looking at, it's important to see them qualitatively. Yes. Because otherwise they see this formulae, okay, yeah, and then they go. But the question is that it's important to see qualitatively, okay? Now,
You were also asking whether it's constant or not.
no, K is not constant.
Constant.
They're
Yeah,
not
so
constants, they're
it's
functions.
just less than 0.
If we look at the Friedman-Robertson-Walker case, then they are constant.
Constant, yeah.
They are constant. Because again, Friedman, Lemaitre, Robertson-Walker, Dost models have the same, this looks like a Friedman equation, but it's an ordinary differential equation. Therefore, all these functions m, k are constants, right? So you don't have these differences.
Yeah.
All the observers will do the same curve, right? Here, because of the radial dependence, the observers do qualitatively the same thing, but not identically the same thing. Okay?
So
Because of the radial dependence. Now, we'll see how these functions are chosen. We'll see that. There are ways.
I was not asking about that. But I'm asking if K is dependent on R and it is decreasing with R.
Yes.
If K is decreasing with R.
We'll see that case in a minute.
So the velocity will also decreasing as the time goes.
Yes, we'll see that.
We cannot say it is expanding.
No. It will still be expanding, but slower. We'll see that. We'll see that in a minute, because what I'm trying to show, now we've seen the case where K is 0 and K is negative everywhere. Now we're going to see the case where K is positive everywhere. And then we're going to see the case when it's mixed. Right? And the case when it's mixed is the one that you're asking. But, okay, we'll see that. Okay? Now, we've seen now K negative and K 0. Okay?
So that R double dot is 0 or non-zero?
R double dot? No, not necessarily 0. For example, look at this. Here you have R dot increasing. And by the convexity, how you have a sign. I think it will be negative. It's going to be negative because the concavity of this curve is like this. So it's going to be negative, right? It's decelerating. Yeah. If we had cosmological constant, then at some point it would do like this, and then it would change the deceleration. Okay. Now, let's look at this case. What happens if K is positive? From the start, if you look at the analytic solutions, notice that in the hyperbolic evolution, which is the case we just saw, R and T are hyperbolic sines and cosines, right? Okay? And in the elliptic evolution, R and T are sines and cosines. So you're already expecting something, a sinusoidal type of evolution. And indeed, this is what happens. If K equals 0, we have the following situation. The Big Bang is something like this. No, in fact, I need more space. Okay, here. This is T, and this is R, and what we have is something like this. And this is what the models, this is what the observers do. This is what the observers do. This is what observers do. And fine, let me erase this thing here. This is R equals 1, R equals 2, R equals 3, etc. This is what the observers do. Because what happens when k equals 0, say when k equals 0, when k greater than 0, then r dot is 0 for a special value. See, if this is positive, then there is a value where r equals, I think it's k over, see, it's very simple. This so it's 0. So r equals 1 over r equals k over 2m over k. For r, let's call r max is 2m over k. Okay? Okay? It's just looking at the differential equation. See, notice, that's the differential equation. If k is always positive, m is always positive.
Okay.
M is always positive, right? It's a sort of mass, so it's
Yeah,
always
okay,
going to
yeah.
be positive. If k is positive, then this derivative will have a 0 for those values, right? Now those are, since m and k are independent functions of r, this will change from observer to observer. But what happens here? What happens here, it's a bounce. Okay. This is what we have here. Notice that this is r as a function of time for different values of r. Right? Etc. Notice how different that this is the point where r dot is 0, right? These are the points where r dot is 0. And at these points, the sphere, the observers are expanding. They reach a maximum radius, big R, maximum value of big R, and then big R starts decreasing, right? So these observers, they rise, they reach a maximum, and then they collapse. Okay, so this is what we would see. Okay, that's clear?
Explain the above graph.
What?
Explain this one.
Which one? This?
Case, yeah.
Well, you have necessarily this. There is a point where r equals 0. There is a. See, this is a. Yeah, I think this requires some extra explanation. What happened? This thing is quadratic, right? Therefore, strictly speaking, what is missing here is this. Plus, minus. K greater than 0. See, r is plus minus this. See, that means that r dot will be positive, right? Will be positive for some of the time. It will be 0 and then it will be negative, right? So, if it is positive, when it is positive, that means that all the observers started from some value equals r. R equals 0. It reaches a maximum value, which is for different observers, and then r dot will be negative, and it will reach again 0. This is what is shown in the upper diagram. Okay?
So time is not a continuous thing after some point.
Time is not.
While looking at this graph.
No,
Time freedom.
this is, we're talking about this time. Because the observers begin at different Big Bang times. But it's continuously smooth. This is a smooth collection of curves.
After it collapsed again,
Eh?
it expands with time,
Yes?
then it collapses
Yes?
with time, and after that it again.
No. Once it collapses, that's finished. Finished. No, it does not bounce after collapse. No. No.
No
Well,
fireball.
There are some people who, like Lyndon Bell, had this idea that you can continue space-time. No, because we'll see that. That's a singularity. Curvature becomes infinite at r equals 0.
No extension.
I think there's no extension, but yeah, no extension.
No
And
extension.
finish.
Finish.
It's like Woody Allen was very worried that when that somebody told him that the universe was going to bounce and then collapse and we would all die. He was very worried until they told him this would happen maybe 18,000 million years from now. Then he could sleep again. Okay?
Because there is a curvature singularity at r is equal to 0,
Yeah.
which is very strong.
Yes, it's a strong singularity.
But it is not solved. The singularity has not been solved, so we cannot say it can be expand again. Or
Look, there's Lyndon Bell tried to devise, it's a professor, well-known professor in
UK.
Cambridge.
Yes, UK.
He tried to and I had once an argument with him.
But he said
But
that.
he dismissed me because I was a postdoc. So I was a young guy, and he's saying that, and I said, no, but that's not possible. You cannot do that. And we had a sort of argument there. Of course, he won the argument. So he was big professor. I was just a postdoc. But anyway, that was another possibility. People try to, for example, quantum gravity is an effort to explain away these things. Is in the sense that you can say singularities are a feature that show
Because-
the breakdown of the theory.
Yeah. It's like creation of classical theory.
Yeah, yes. All theories have their limits. So
Yeah.
I say GR finds a limit there, and then there's another attempts by a colleague of mine, which are doomed. But I already know they are doomed. They put complex numbers. This relativity is described for real numbers. So they have invented some horrible, untasty dish called octonion GR. And in that, they say Einstein, they are Germans. So you know, Einstein in German means one stone. Ein in German is one, Stein is stone. So Einstein is one stone. So they have a paper called Einstein, zwei Stein. That means one stone, two stones.
No, but in
And then in this octonion gravity, then there are no singularities. And they think that's very good. However, we know that black holes do forms exist, and they. But we exactly don't know what happens at the extremely critical phase. Maybe some quantum gravity.
No, but in spherical collapse means nowadays it's accepted by Hawking also that it can be a black hole or it may be a naked singularity or fireball.
Yeah, we really don't know. All what we know is that there is a strong indication that there are astrophysical objects in which extremely critical phenomena happen, that are manifest themselves by huge radiation and so on. But intimately to be there, we still don't know what's going on.
No, but theoretically it is already proved, no, about naked
No,
singularity.
you cannot prove this thing. No. You mean the naked...
Naked singularity, theoretically it can be proved. Means, it is proved already.
No. We'll see that again.
No,
that's-
but she was trying to say that if you take any gravitational collapse model
Ah,
with like Tolman Bondi or any other
Yeah.
matter, it leads to black hole as well as naked singularity.
yes,
Starting with the regular data.
yeah, no, I know, but, yeah, for example,
But any
I know
model you
people
take,
who,
I know.
no, but those proofs exist, but they don't, it's not, they don't carry on to nature. Why? I'm saying you can take an LTV model, like for example our colleague Pankaj Joshi has done, and you can prove that, yeah, naked singularities emerge under data that are not so physical and so on. But where is the limitation of this? The limitation of this is that is the model itself. You cannot realistically say that matter undergoing critical collapse will be dust. Flat, period.
not only does,
Not only does,
any matter.
Any matter,
Any matter,
in
it says
your
even if you take include stress, pressure,
Yeah.
then also it will lead to naked singularity.
Yeah.
Anyway, I think those conditions are not sufficiently generic. Anyway, let's not deviate from the subject. Now we've seen what happens when K is positive and when K is negative. Okay? Now, let's see what happens when they are mixed. Okay? So the idea here would be to suppose that K, see, we're going to assume the following. We're going to assume that K is such that it is positive for a certain domain that goes from 0 to R to some boundary. Then it is exactly 0 for R equals the boundary, and then it is negative for R greater than the boundary. Okay? We're going to assume this behavior. And so what we will get is a mixture of these two. Okay? And it will look like this. It will look like this. Can I erase this? People are...
Yes.
Okay? So it will look like this.
So can we have a universe which oscillates about Big Bang time as origin?
No, not with these models. With a cosmological constant, you can have oscillations, but not with these models. These models have very simple dynamics. Either they expand, reaching zero velocity, they expand, reaching non-zero velocity, or they expand, bounce, and collapse. That's it. No oscillation. No, it's not allowed by this equation. Okay? Now, what we would see here is the following. This is the boundary, right? So, observers here, all observers here perpetually expand. Sorry. All observers here are perpetually expanding. But observers here are collapsing, right? So how you continue this? It has to do something like this. It has to do something like this, right? So, all these observers that are in the inner region where K is positive will expand, bounce, and collapse. But all observers that are in this region will perpetually expand. Obviously, look, the observers here are expanding, and they're expanding, and they take a very, very long time to collapse. Very long time. The closer you get there, the longer time they get to collapse. But in the end, they collapse, even if it's very large. And here the observers, this is the first observer that never collapses. And these other observers go faster and faster and faster. Now, the time where they bounce, this is the time where they bounce. See? Observers reach this point and then they bounce. They reach this point, and now the further we get to the border, the longer it takes them also to bounce. This will be seen clearly in this diagram, right? So we can identify this region. This is a very simple model of a black hole that is embedded in an expanding medium, right? And it's a smooth model. It's now, this is clearly seen here. This is clearly seen here. See, what happens here is as follows. The observers that are near here collapse. This one takes a longer time in collapse. This one takes an even longer time. Let me remove this, because this takes a long time in collapse. This one will take an even longer time to collapse. This one will take an even longer time to collapse, right? And here would be the first observer that does not collapse. This observer is the first one that does not collapse at RB, right? And these ones are expanding perpetually. This is the image, right? See? This is, for example, this here, k equals 0. Here, for example, k equals positive, but small. And this one is k equals negative, but small, right? Okay? But essentially, as long as k is positive, the observers will collapse, even if it takes a long time, they will collapse. So there comes a point, if I tell you the universe is going to collapse in 1,000 trillion years, that's practically, for physical purposes, it's never going to collapse, right? So observers that are here, just it will collapse, but it will take so long that, but anyway, mathematically, the model, we distinguish model and physical reality. The model says that these observers, as close as you want to get to k equals 0, they somehow will collapse. The ones in k equals 0, first one that doesn't collapse, and the ones continuing. So this is, we can have a mixed situation. And this is a very nice model. This is a nice model, the simplest model you can do of formation of a structure or a black hole that is surrounded by an expanding medium, right? And all these, yeah?
You said surrounded by expanded?
Expanding medium.
Medium.
Expanding dust. It's all dust. But the dust will collapse in an inner region and continue expanding in the exterior.
You mean to say that dust will come closer and it will form a kind of mass?
It will form a black
dense
hole.
Mass.
No, a black hole.
Black.
It will be denser, then form a black hole. R equals 0 is a black hole. See? Now, people can ask, and where is the horizon and so on? You can compute the first here it's all matter, so there's no event horizon, only apparent horizon. And that's a subject in itself, which I think that when this guy comes, this German guy comes, he will talk that he will explain that carefully.
We can have tea break.
Yeah, let's have a tea break, and then we
And
continue.
then,
We form now a black hole outside.
no, first we go down. Let's go down first, we'll have group photograph.
For group photograph.
And then we can come for tea.
We've already discussed the qualitative behavior of the solutions. They're very simple. And that's why people like them. But still they are powerful enough to describe many features. Here, I set up cosmological constant to 0. If the cosmological constant is non-zero, then there are more possibilities. For example, there's a possibility that dust layers expand and then they are asymptotically static. It's unstable, but it's possible. Then there's a possibility that layers come from infinity, bounce, and go back to infinity, which would be the opposite from emerging from a singularity, bounce, and returning to a singularity. You can have a situation like this, right? And there are other possibilities which we will see. I'm going to show you in the course how to choose these functions, because now you have nk and bank time. So in theory, you can invent any function, say, well, sine, cosine, hyperbolic sine, decreases, increases, whatever. And maybe you get some decent models by accident. But I'm going to show you how to choose these functions in a physical way, of course. But be patient, we'll see that. Okay? Is it on? Ah, yes. Okay, now let's see the next one. Kinematic evolution. We've already seen kinematic evolution. We have parabolic and hyperbolic. Parabolic k equals 0. Hyperbolic k negative. Okay? The dust layers simply perpetually expand, or they can perpetually collapse also, depending on how, but we're not going to see the case when there is perpetual collapse, but it's possible, mathematically possible. Then elliptic dust layers then expand and then collapse. This is strictly speaking with 0 cosmological constant. Now, there are models or regions, see? Since k is a function of r, a single model can either have the same kinematics everywhere, which is the first cases that we saw, right? Same type of kinematic behavior, or it can have different kinematic behavior in different moving layers. See? We can have, like, look at this. In this case, all dust layers that are labeled between 0 and r subindex b, they have elliptic dynamics. That is, they expand, bounce, and collapse. And all the layer exactly marked by r equals b, that single layer, which is a spherical layer, all these dust layers are spherical. That layer will have parabolic dynamics, parabolic kinematics, meaning that it will expand forever with terminal velocity r dot, with terminal r dot velocity equal to 0. And all the layers that are marked by r greater than rb will have hyperbolic, right? So you have the possibility that one single model will have the three different kinematic behaviors. And of course, you can have more regions and more combinations of them. That is also possible. But this is the most physical situation in which you have different kinematics. The most physical one is an inner region that will expand, bounce, and collapse, surrounded by an external region that will be expanding forever. And this is in the same model, in one single model, just by the choice of the parameter k, right? So that's an important thing. These are some numerical graphs. This is the time, and this is radius, and this is big R. So this is parabolic and hyperbolic. Well, what they do is that this thing simply grows, that's all. The central region is R equals 0 at the center. There are conditions that guarantee this. There are regularity conditions. These functions m, k, they have to have special behavior near the center. There are regularity conditions that we will see. And this is what happens in elliptic dynamics. The layers expand, reach a maximum, and then collapse. And this is what happens in the mixed case. In the mixed case, you have a region in which this kinematics happen, is this region here, and suddenly you have an exterior region where this thing happens. So these are the three, essentially, three different kinematic scenarios that we have. Now, the spatial curvature and kinematics. This is a Ricci scalar of the rest frames. Hypersurfaces of constant time, which are orthogonal to the four velocity. The Ricci scalar is this. So as you can see from this expression, if k equals 0, that means that this scalar is 0. These parabolic regions are spatially flat. If this is negative, then this means that hyperbolic regions are negatively curved. However, here, notice that the implication only goes this way. If that is, all positively curved regions are elliptic, but some elliptic models admit regions with negative curvature. So this is the relationship between the spatial curvature defined in a covariant way, because this is a Ricci scalar of the rest frames, and the sign of k. K is closely related to the, well, and this is very similar to what happened in Friedman-Robertson-Walker models. Remember that this capital K, which is a function of R, is a generalization of the Friedman-Robertson-Walker constant, right? Now, in Friedman-Robertson-Walker, it's a constant, so it cannot change signs, right? This is a generalization, and just as that constant is related to the spatial curvature, the function k is also related to the spatial curvature, but in a more complicated way. Topology of the rest frames. Yeah. Now, what I mean here, the rest frames are three-dimensional surfaces, right? Okay? So to look at them, you take them and you embed them in R4. You embed them in a space, in a Euclidean space of higher dimension, one higher dimension, right? You can embed them. At least you can immerse them. Now, these ones you can embed them. It's an embedding. But now, I'm going to, once you embed them, you can appreciate their topological class, their homeomorphic class. However, these are not the only classes that are possible, because topology allows, you can have very, very complicated topologies with the same differential geometric structure, right? But let's look at the simple topologies only. Now, this is the simplest topology here. Simplest topology is R3. This is a center of symmetry. See, these diagrams show you the following. These diagrams are an embedding. Of course, this is a three-dimensional surface, but I have to show it as two-dimensional, right? So what we're plotting here is big R as a function of small r for phi varying. Theta is kept fixed, right? Do you understand what I'm saying? You want to embed a three-dimensional space in 4 dimensions. Our senses cannot see. See? So in order to do that, we have to display 1 dimension less, right? So what happens if you set one of the angular coordinates, for example theta, you set it to pi by 2, right? Then you have 3 coordinates, right? Space, radius, and phi. Time, radius, and phi. Since time is constant, see we're looking at constant time surfaces, then it's only r and phi. And this is what I'm displaying here. I'm displaying here r, and the angle here is phi. Okay? And this is the way these surfaces would look if placed in R3. They would look like this is topologically equivalent to R3. Here is the center of symmetry. Center of symmetry is a point where r equals 0. Small r. Small r equals 0 is the fixed point. See, each one of these circles is representing a 2-sphere. It's a circle, but it represents a 2-sphere. So here I'm piling all the 2 spheres. These are orbits of the group. The orbits of the group are these circles. There are 2 spheres, but I'm representing them as circles. Okay? Is people following me? Yeah.
There are 2 spheres.
Yeah?
When you say there are 2 spheres, what do you mean by that?
They are 2 spheres. The orbits of the group are 2 spheres, 2-dimensional spheres. Okay? But I am representing them as 1-dimensional sphere. Okay? Because otherwise I wouldn't be able to represent anything. I can only represent in an image of 2 dimensions. I cannot represent one of 3. Right?
So it is an external surface or an internal surface?
What?
That figure.
This one?
Yeah.
This is a 2-sphere, and the collection of 2 spheres make up a 3-dimensional surface. This whole thing, which looks like a 2-dimensional surface, is a representation of a 3-dimensional surface.
Now I want to ask whether I am looking into the glass or I am looking outside the surface of the glass.
You are looking outside,
Okay.
because we're placing this 3-dimensional surface in 4 dimensions. It's not a physical space, it's a mathematical space. You are not able